Rotational dynamics is now just the analog in rotation for dynamics, when we talked about forces and accelerations being related. Now what we get to say is that torque causes an angular acceleration. And the equation that we're going to write is that the angular acceleration of our object is defined as the total torque, net torque, divided by the moment of inertia of our object. Now the direction in this case, when we had forces and accelerations, these were vectors, and we would think about their x and y components. Now we just think about clockwise or counterclockwise, and we can use signs to do that, where clockwise is our minus sign, counterclockwise is our positive sign. So if the net torque is positive, then the acceleration, the angular acceleration must be positive, which means they're both counterclockwise. So this should hopefully make sense. If we've applied forces to a bunch of different spots on our object, that we then say that each of these forces could make the object rotate, but the entire object must rotate together. So that's how we actually get to saying, okay, what I care about is my net torque, which of these individual torques is winning out, and then that leads to a angular acceleration. It will start spinning, or it will change the rate that it's spinning. Now, this is completely separate from talking about a net force that is making the entire object have a linear motion. We will talk about that later, but right now we are only concerned with angular acceleration and rotation. I want to talk you through the setup of a calculation in the book that's related to this. We have two rockets that are connected to a tunnel. And we're assuming that the tunnel is a rigid object, so its length does not change, its shape does not change. And we're approximating it as massless. It, of course, does actually have mass, but the mass is much, much smaller compared to the mass of the individual rockets. So in this case, you have two rockets that at the same moment turn on their thrust, so you have two thrust forces, and we then want to think about what's happening. One thing to ask is whether there's a net force. Note that F2 is 50,000 newtons, F1 is 50,000 newtons. If I chose to approximate the whole thing as a particle, as a point particle, I would then say I have F1, I would have F2. We see that F1 is equal in magnitude to F2, so in that case, Fnet is equal to 0. So this is why it's important to think about an extended free body diagram where you're actually showing the shape and size of your object, because we cannot approximate this as a particle and understand what's happening. It is still true that the net force is 0. The center of mass of this object is not going to start moving because the net force is 0. However, this isn't really a helpful way to analyze what's happening here, because really we want to think about what's happening rotationally. So what is the point that this is going to rotate around? We believe that it's going to start rotating. We have to say where. Now, if we were told that it was somehow fixed by a bar to a planet or something, we would maybe have a pivot point in that case, right? In some problems, you're told what it pivots around because there's literally a hinge or an axle there. In this case, there is not a hinge or an axle. In that case, if it is free to rotate around whatever it naturally rotates around, that's the center of mass. The center of mass is our pivot. So this is an important idea. If your object is free to rotate around whatever point it wants to, it's going to rotate around the center of mass. And when you're first setting up a calculation, you must identify what that pivot point is. So in this case, it's the center of mass. How do you know what the center of mass is? Well, we've said that the tunnel itself is rigid, but we have two rockets that actually have different masses. So when you've drawn this picture, even if you don't know the specific position of the center of mass, because rocket 2 is more massive, you can assume that the center of mass is going to be closer to rocket 2. To calculate the center of mass, we use this equation because in this case we have two discrete masses to worry about. It's important to remember that you must define your x-coordinate system to actually figure this out. And a convenient choice would be to have it aligned with the tunnel so that this becomes a one-dimensional problem. And in this case, we can set the left rocket to be at a position of x equals 0. The rocket 2 is then at a position of 90 meters, because that's the length of our tunnel, and we can plug in values up here to get what the center of mass is. When you plug in values, you end up getting 2/3 of 90 meters, which is 60 meters. So we then have that this position equals 60 meters. So that is the point that it's rotating around. The problem didn't necessarily ask you explicitly to calculate where the center of mass is, but you can't solve the problem if you don't actually do that. So then, we need to find a net torque. So the net torque is going to be the sum of the individual two torques. Now this is where it's important to not just use F net. We've said that net force equals 0, which is why this is only rotating. We then have two torques to worry about, and we want to get our signs right. So for the torque from rocket 1, we see that the radial distance and the force are perpendicular, so we just can multiply that distance times the force. The angle itself is 90 degrees, sine of 90 is 1. So note that if I just think about this force pushing, which way is this going to turn? This rocket would be going counterclockwise. That's positive. When I look at my second rocket, it would be pushing this way, which is also counterclockwise, so that's also positive. Now, this picture was already labeled R1 and R2. Keep in mind that the distance that goes into the torque equation is the distance that each force is applied from the pivot point, which is this case the center of mass. So you wouldn't use 90 meters for it, you just want to use the distance from the center of mass. Lastly, how do we calculate alpha if what we actually want to find is the angular acceleration of the whole system? Well, now we say that angular acceleration is going to be my net torque divided by I. Well, net torque in this case is just R1 F1 plus R2 F2. But what is I equal to? This is the moment of inertia of our system around the center of mass. And in this case, again, it's a discrete system, so we can calculate I fairly simply. It's the mass of rocket 1 multiplied by the distance that rocket is from the center of mass squared plus the mass of rocket 2 times the distance that is from the center of mass squared. So how you would find then your angular acceleration is dividing your total torque by the moment of inertia. So again, if you were given this situation and told what is angular acceleration, you would have to recognize along the way that you need to calculate the center of mass and the moment of inertia. In addition, that's just in terms of finding torques and everything else. So please be careful on rotation problems. There's a lot that you frequently need to calculate to do them beyond just what is asked for.